In this video, we're going to start to look at some of the properties of solids. And in order to do that, we're going to make a flowchart that'll help us classify the different types of solids. So the first choice we're going to make is we're going to look at the chemical formula. If a chemical formula has only metals, if it has only nonmetals, or if it has both. That's probably the easiest thing to tell just by looking at a chemical formula. If I've only got sodium and magnesium, well, those are only metals, and so we're going to go into this metals tree. What that's going to get us is metallic solids. And metallic solids are going to have high melting and boiling points, high melting points, high boiling points. They're going to have a crystal structure, and they're not going to dissolve, so non-soluble. Metals also have this very interesting quality of being malleable, which means that if you hit them, they will bend instead of breaking. And it's going to be due to the metallic bonds that are inside of that metal. All of those electrons in that electron C model are going to easily move around any of the atoms nearby, and so there's no rigid bonding structure. All right, so now let's look at if we have both. If we have both metals and nonmetals, that's an easy classification as well. It's going to be ionic. We're going to have ionic bonding, okay? And now what's going to determine the strength of that ionic bond? Well, that's going to be two factors, and we'll look into these a little more in just a bit. The two factors are going to be the ionic radius and the charge. Okay, so ionic particles, ionic solids, they're also going to have high melting points and high boiling points. They're going to be a crystal structure, but they're going to be soluble. They're often going to be soluble, and they're going to be very brittle. If you hit an ionic substance with a hammer, it is going to shatter. It's not going to bend, it's going to break. All right. So those are the two easiest ones to identify, metallic and ionic. But if all we have is nonmetals, we're going to need to do a little work. So let's go here. If we've got nonmetals here, then the next choice we need to make is, does this have an actual molecular structure, or is it a network covalent molecule? What does that mean? Well, we can have substances like diamond. Diamond is going to be made of pure carbon. And it really isn't made of a bunch of carbons that create a set chemical structure. It's not going to be, 5 carbons bonded in a row and then all of those stacked on top of each other. It's really going to be all the way down to the molecular level, billions upon billions of carbons all attached to each other. Because carbon can keep doing it. It can make four covalent bonds. And if it just keeps going indefinitely, then it makes something like diamond. Another setup for this, if we didn't have the pressure and temperature making diamonds, this could be diamond, or it could be something like graphite, or it could be something like coal. Coal compressed with a ton of pressure and a ton of temperature is going to cause it to become a diamond. So we can have these substances where something like a diamond, where it's going to be this huge molecule, it's just pure carbon. It's just a bunch of carbon molecules all compressed together, all covalently bonded. So there is no separation of molecules here. A diamond is just one giant molecule. Other things that are like that are glass or quartz. This is actually a fairly common phenomenon. So let's write that up here. We're going to have, if we have nonmetals, we could have a network covalent molecule. And so for these, we're also going to have high melting points and high boiling points. And that's going to be because what we're breaking when we melt that, or when we boil it, when we melt it, is a covalent bond. It's just covalent bonds, which are very strong holding these things together. So what if we don't have a network covalent molecule? What if we have something else? Well, then we're going to have a molecular bond. And in order to differentiate these, we're going to need to split this up into a few more categories. So the first question we're going to ask is, does this have hydrogen binding? Does it have, so let's ask that question, does it have H to O, H to N, or H to F type bonds? And if it does, well then our force that it's going to hold this solid together is going to be hydrogen binding. And so if it's got that hydrogen binding, it's going to be a fairly strong bond, and it's going to have a medium melting point. So a mid melting point and a mid boiling point. So if we don't have one of these types of bonds that gives us hydrogen binding, the next question is, do we have a polar bond? Do we have polarity? And then if we do, so let's say, let's go to the right with yes, to the left with no. If we do, then our next question is, do we have symmetry? If our bond, if our molecule is symmetrical, that would cancel out that polarity. So do we have symmetry? And so if we have polarity and we don't have symmetry, then what we land with is a dipole bond. These are going to be weaker than hydrogen binding, but they're still going to have a mid melting point, medium melting point, medium boiling point. This might be solvents like acetone or dichloromethane. And then we can have something that has no polarity, then the only thing that's left is going to be London dispersion forces. And these are going to have very low melting points, very low melting points, very low boiling points. This is why things like nitrogen and oxygen are just gases at room temperature. It takes a lot, it's got to be really cold for that London dispersion force to be enough to hold those together. But what's going to determine the strength in those London dispersion forces is going to be the length of a chain. So something like, if I have something like a really long carbon chain, this could all bond together. And this is what happens in oils. If I have something like butter or coconut oil, that it's going to be a solid because we have really long chains of carbon and hydrogen, just carbon to carbon, and each one is bonded to a bunch of hydrogens. The other determining factor in the strength is going to be number of electrons. If I have more electrons, my London dispersion force is going to go up. The determining factor in the strength of a dipole, that is going to be the electronegativity difference. There we go. There's a nice long flow chart here that'll help us just categorize different solids so that just by looking at a molecular formula, we could start to identify, hey, what are going to be some of the qualities of this? So when we look at metallic and ionic, one word should really stick out, this crystal word. What does that mean? What that means is that on the molecular level, it's going to be very orderly. And so when we have something like an ionic solid, if I've got sodium chloride, it's going to have a bunch of molecules all arranged in an exact order. It's going to form this very clear structure. Now, if I have something like glass or quartz, both of those are going to be made of the same thing. They're both going to be network covalent molecules, but both have this SiO2 as their average formula, and we end up with Si bonded to oxygen, bonded to Si, which is bonded to oxygen on all sides. And in a quartz crystal, this is all going to be very, very orderly. All of these bonds are going to have the same length. And so we call that a crystal. And so in quartz, a network covalent solid is going to be a crystal. But in glass, we're going to end up with these very different bond lengths. We might have a little more randomness here. And because of that, this is going to have a very high degree of fragility. We call this amorphous. And because it's amorphous, if I hit this with a hammer, well, it's going to be very fragile. Some of these bonds are going to be stretched out, and so this bond is likely to break if it experiences a force. And when it does break, it's going to break in jagged lines across these different bonds. And so that's why when we break something like glass, it breaks in these completely random ways. Or if we break something like quartz, it's going to break in these clean faces. So that should be the basic stuff that we really need to know about all of these different solids. In the next video, we're going to start to look at how do we rank the strengths of these forces. And we're going to be revisiting the idea of this flowchart.